In this video, I'm going to talk about topic 3, electric potential. We're going to go through some questions and I'll give you some tips on how to solve them. And the first one is very similar to a question that we did in the previous topic. It's asking the unit for the electric field. We've already know that it's N over C, which is coming from the formula FEC, but just to quickly remind you, the other formula is VED. V equals ED. This is how you get this unit. We want E, so I'll just change that to get V over D, and I'll just put the units in now. V stays as V. Volt is the unit for V. And D is meters, so you can see there's a division. Volt per meter, so that's wrong. This one is correct, and these two are not necessary. So this is the unit that we will use. Which of the following are scalar? So this is a pretty simple question. Force is not, that's a vector. Field is a vector. Potential is a scalar, and potential energy is a scalar. That's great, so 3 and 4. So what that means is if you're doing any calculations involving these, you must include the minus if it is a negative charge. For these two, you do absolute values only. You do not include the minus. Alright, so that's been cancelled. Electric field lines go from, if you remember, it goes from plus to minus. You know this from the charges that we did in the last topic. It goes like this. The idea is the same. It goes from the higher potential to the lower potential. That's how it goes. So higher potential to lower potential. Potential is the V, by the way. That is the V, which is joules per coulomb. Now, positive charge is released, moves along the electric field, it goes to a position of something. And this one here, negative charge, also does the same thing. So before I answer them, let's quickly understand what happens. I'm going to draw a positive and a negative. Sorry for the messy writing here and the messy drawings. Plus, and then the minus. What happens is you have a field going from plus to minus. You can have it either direction. I just picked it to be like this. So, before even understanding what happens to the charge, the first thing you can realize that this has a higher potential and this has a lower potential. So, the idea here is, if you are on towards the left-hand side, my V will always be increased. If I'm going to the right-hand side, my V will always be decreased. This is potential. Now, the potential energy depends on the charge and where he is. For example, if I placed a positive charge here, or even here, you can compare their energies. This charge is not happy here at all. He is quite angry. That means he has a lot of potential energy. He wants to run away. He wants to go this way. So his energy, the U for this person, this will be quite high, until he gets to the other side. Over here, he is very happy to be here. He is exactly where he wants to be. So his U, his energy, will be decreased as he goes along to the right. So, similar idea now for the electron or any negative charge. For example, if I placed a minus charge here and I placed the minus charge here, which one do you think will have the most potential energy? You will find that he does not want to be next to this one, so he is not happy at all. I always draw these little faces to help me remember. So his energy on the right-hand side will be high. He does not want to be here. On the left-hand side, he is actually very happy. He is attracted to the plus, so he is happy. He does not need any energy, so his energy will be low. So this is a little idea. Maybe you can draw it for yourself when you see a question like these two that are coming, and that will help us. So, based on this drawing, let's answer the question. A positive charge moves along the electric field line. What does that mean? It's literally going from plus to minus. It's following the field line. Okay, so these are the things that I know about it. It goes from high potential. So actually be careful, because it says goes to where? So from high potential to low potential. So it's going to go towards low potential and low potential energy. This is good. Now why is this good? Because on the right hand side, when he finishes, his energy is low and the potential is also low. So that means those both are correct answers. Checking the next one, it says same thing, it moves along the field line, so not against, it's going in the same direction as a field line, and it moves to a position of. So electron also moves to the right. And now you can see that he is increasing his energy, and the V, of course, is decreasing. So the U and the V, let's have a look. We're going to see this here. He's not happy where he is going, so his energy will be high. So that means he will be going towards a lower potential and high potential energy. So that means we'll be doing a lower potential and a high potential energy. He does not want to be here. His energy is high. Okay, so that is B. A positive charge, moving around, we're trying to figure out the work done. Well, you can see that the work done only depends on the final minus initial displacement, from start to finish. This is all that I care about. It doesn't matter if I go on all these squiggly lines, it doesn't really matter at all. As long as I finish here and here, that means that all of the work will be the same. So in this case, D is the answer. Work is the same on all the paths. So the same idea over here, if you notice that they all start here and they all finish here. So it doesn't matter if I go to infinity and beyond, I will have the same work. So that means this will be E. Over here, you have 3 pairs of plates. You need to find the magnitude of the electric field between the plates and rank them from high to low. So in this case, we can just have a quick look right now. And what we're going to do is see the difference. The only thing changing between them is the V. So I can just do the V final minus V initial. So I'm assuming this is going to be the final, this is going to be initial. So we will do 150 minus 50. 150 minus negative 50. That basically means the difference there is 200. Okay, this one here, same idea, 200 minus 20, 200 minus 20, which just basically means 220. Why am I doing this? I'm doing this because to find the potential difference is V final minus V initial. Okay, so that is going to be 220 over here, Mr. 2. Over here, same idea, minus 500, minus 300, and we are going to end up getting negative 200. This is asking about the magnitudes, okay? So the magnitudes means value only. I do not care about the direction or the negative. These two are the same, and this one has a bigger value. So magnitude 2 is greater than 1 and 3, which are the same. There we go. Over here, 2 plates are held at this potential, and if you have this area and you have the distance here, what is the magnitude of the field between the plates? Okay, so in this case, we're not really interested in the area. What's that going to do? Nothing for us. Because if I want to find the electric field, we can just use our formula VED. V equals ED. E is V over D. So I'm going to do that. And that's going to be V final minus V initial. So you're going to subtract these two values together. So what I'm going to do is I will do, usually it's supposed to be negative, and then final and initial will be minus, and then you'll have 130 minus 220. So these minuses will actually just cancel out anyway. And you'll divide that by 7.3 millimeters is not good, so you're going to have to put that into meters. 7.3 times 10 to the minus 3. By doing that, you should put this in your calculator and you'll get 12,000 newtons per coulomb. That would be your answer there. Okay. Next question over here, we're going to see a proton is placed between A and between B. So we're going to have A and B. And so this is A, which is minus 20, and this is B, which is plus 20. So I can see that the field will, that's supposed to be plus 20, 20. This is the field must be going like this, from plus to minus. So this is the field. What will he do? In the middle is 0, fine. I place my proton here, where will he go? I release him. Does he want to go towards the minus or towards the plus? Well, of course he is a positive, so he will go towards the minus. He'll go towards A. Now, he will not just go on a constant velocity, he will accelerate towards A. Why? Because F equals EQ. Fick. This is a force. A force makes any mass accelerate. Newton's second law. A force makes a mass accelerate. The proton accelerates. So the idea is he will accelerate towards A. All right. You don't need to use the formula, it's just me explaining why it accelerates and not constant speed. Okay, so over here, an electron is accelerated from rest, okay, starting speed is 0, through a potential difference of this, so you do not need to do final minus initial. What is the final speed? Okay, so in this case, we know that energy is energy, right? So if I calculate my energy, and that is going to be the same thing as my kinetic energy that we know from previous grades. The energy, W or U, equals QV. Q, big V, this is voltage. And kinetic energy, you might remember, is a half m small v, which is speed, squared. Q being the charge of the electron, 1.6 times 10 to the minus 19, multiplied by 450 equals a half of the mass of the electron, 9.11 times 10 to the minus 31. You'll get the numbers on the front page of your exam. Multiplied by the speed, squared. Shift solve, you will get yourself the speed, try it yourself, and you should get 1.3 times 10 to the 7. Use your calculator to solve it. Or you can rearrange the formula if you want. If you want me to show you how to rearrange, I'll quickly do that right now. That becomes over here, so it becomes 2QV, and I'm going to divide by mass, divided by, because I have to divide both sides by mass. That way this will cancel, over mass, and then that's for v squared. That's for the small v squared, so I'm going to do the square root of both sides to cancel it. That is what I can do if I wanted to rearrange the formula to get the v. Or use your calculator. Either way is fine. So in this idea, 5-volt batteries connected to parallel plates, electrons accelerated. What is the kinetic energy just as it reaches? So idea is simply this. This and this are equal to each other. Whatever potential energy I started with will convert to kinetic energy at the end. So I do not need to do a half mv squared. I can just do KE, that's a K by the way, okay? KE equals U, which is simply QV. You're going to have 5 multiplied by an electron, 1.6 times 10 to the minus 19. Solving that, you should get 8 times 10 to the minus 19. And I'm going to stop that there before I move on because the video will get too long. Thank you.